So first, we're gonna check out the course and see what's been added and what the new module looks like if you haven't done that already today. So here we are. This is what you guys should be able to see at this point in the course. All right, we've got our calendar and our modules here. As you can see, I've already started updating today in the calendar. Here's the presentation for today. I've got the recordings going in there from earlier today, and yours will be added later. If you have not completed the survey from last week, all right, the one to help me get better communication with you, please do so. I would like that information. If you already have, thank you. I appreciate it. And here is our new module, Chapter 6, Random Variables. We have all the resources and stuff loaded up into Chapter 6 module already. The only thing I'm still working on are the assessments. All right, those should be ready hopefully by the end of the day tomorrow. I'm almost done with the multiple choice part. I need to get the free response question / self-assessment put together. And then those will be available. All right. So just take a look at the modules themselves, or itself, Chapter 6. This is kind of what the new modules will look like, right? The calendar will essentially organize what we do each day. And the modules will contain stuff for specific chapters and sections. So as you can see, we have Chapter 6, Random Variables, and the 3 sections that are in Chapter 6. Today we will be doing the lesson on discrete and continuous random variables. If we go into notes and resources, right, this is what our notes and resources look like now. All right, at the top you see we have notes. This first thing is essentially the study guide, pre-made set of notes for section 6.1. All right, and that's what this looks like. It is something that you can just click into and look at. You can print it out if you like. It is for you to use however you see fit for yourself. It's full of lots of good stuff. It's got examples, it's got definitions, formulas, all that fun jazz in one spot for you. All right, so that is what that looks like. All right, I have the presentation from today. It's already been loaded up into here. Valentine, yes. You had your hand up.
Oh, I have dude, math too. I don't know why. No, about that. Could we write it down, the class notes, on a piece of paper?
Yeah.
I'm just asking.
Yeah, you can. I encourage you to write your notes down. I'm just having more like some stuff that's kind of available for you as like a resource, just for as like reference. I would recommend looking through the like study guide and taking your own notes based on that as well.
Okay.
But it's just another resource. It's another like essentially the study guide is I went through and read the chapter and put together the things that I think we needed from the chapter.
Yeah.
All right.
Okay.
But yeah, I encourage that you write stuff down. And if you don't have a notebook, again, we have some at Orange Glen. They have the graph paper composition books that are available for the math students for free. So if you don't have a notebook and you need a notebook, you can stop by the school and ask for one. It is free. So
okay, thank you.
You're welcome. All right, and so then, yeah, we have the presentation from today is already up here in our notes and resources for 6.1. We have the 3 AP daily videos that apply to today's lesson and to section 6.1. There are some worked examples from the textbook. We'll see some of this today in today's class. We'll see some of these examples, but it's not necessarily as lively worked out. And we also have some calculator instructions for 6.1 showing how to input random variables into the calculator. So if that's something that you want to become more familiar with, there's a video, or you can just look at images of how to do it. Those are options. All right, so that's what the notes and resources section looks like. We also have the practice problems and solutions in each section. Right, we use 6.1 as the example. We have the problems, we have the solutions. Right, and again, just like the notes, this is just a list of problems that you can try and practice with. I recommend trying the problems first, seeing if you understand how to solve them or how to set them up, even just what they're asking. And then you can check your work with the solutions. All right, so there's problems and solutions. The solutions don't necessarily show how to do the calculations, but they will say what the proper result was supposed to be or was supposed to look like. So it's a way for you to check your understanding on your own. So that's another resource for you guys, as many of you asked for more opportunities to see more different types of problems and things like that. We don't always have time to do that in class, so I wanted to provide opportunities for you to do that on your own if you wanted to. It's not required, it will not be graded. It's just an opportunity to practice. All right, we will have opportunities to do practice work in class during our live sessions. I'm building in time for that this semester. All right, so that's what these are going to look like. Is there any questions about the resources for Chapter 6 or for the new modules? Okay, excellent. So, next, we're going to get into the lesson. Today's lesson will be on section 6.1. If you are taking notes, I recommend that you get your notebook ready. This is primarily a note-taking day. All right, so here we go. Chapter 6. Random variables. Our first section, section 6.1, is discrete and continuous random variables. All right, today, what we are hoping to accomplish and what we're hoping to learn is that we'll be able to compute probabilities using the probability distribution of a discrete random variable, calculate and interpret the mean, otherwise known as the expected value, those terms are interchangeable now at this point, of a discrete random variable, calculate and interpret the standard deviation of a discrete random variable, and compute probabilities using the probability distribution of certain continuous random variables. All right, if you don't know what a random variable is, you're in the right place. We're going to learn that today. So, random variables and probability distributions. A probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. All right, for our initial example here, let's consider tossing a fair coin 3 times. We're going to define the variable x, it's a capital letter X, to be the number of heads obtained. So this variable x just keeps track of how many heads show up when I flip a coin 3 times. All right. In this scenario, there's 4 different possible numbers of heads. I can have 0, 1, 2, or 3. Right? This right here is the probability model. It shows me the possible outcomes. Right? I can get 0 heads, which means I had all 3 tails. I can get 1 head, where I can have a head show up first, second, or third, and the other flips are tails. All right. We can have 2 heads, in which case my first 2 tosses are heads, last is tails. 2 heads with the tails in between, or the first one is tails, last 2 are heads. Lastly, the last possibility is 3 heads, in which case I got a head on each toss of the coin. So X can take on any of these four values. Then we have the probability distribution, and this shows the four different possible values for x, 0, 1, 2, and 3, paired with their probability of occurring. I have a 1 in 8 chance of getting no heads, a 3 in 8 chance of getting 1, 3 in 8 chance of getting 2, 1 in 8 chance of getting 3. Right? So again, it's describing the possible outcomes and the likelihood that those outcomes occur. We can also show this distribution as a histogram, right, where we have 0, 1, 2, and 3, and the height of each bar shows the probability as a decimal. A random variable takes numerical values that describe the outcomes of some chance process. X is the random variable. It's taking on the values of 0, 1, 2, or 3, which describes the number of heads. That's our chance process. The probability distribution of a random variable gives its possible values and their probabilities. That's the table here and the histogram here. Right, so first we're going to focus on discrete random variables. Right, when we're talking about random variables, there are two main types of random variables, discrete and continuous. Right, we'll discuss what a continuous random variable is later in the lesson. If we can find a way to list all possible outcomes for a random variable and assign probabilities to each one, we have a discrete random variable. Right. So if I can list it, like in the previous example with the tossing a fair coin, I can list the different outcomes, right? And each outcome has a specific probability I can assign to it. That is a discrete random variable. So our definition is here. A discrete random variable x takes a fixed set of possible values with gaps between, meaning it's like counting numbers, right? There's a gap between 0 and 1. There's numbers that exist there, but I'm not counting those. Right. The probability distribution of a discrete random variable x lists the values x sub I and their probabilities p sub I. So this is essentially like the table here. We have the values that x can take on, which would be x sub 1, x sub 2, x sub 3. Right. The numbers here, right? The sub 1, sub 2, sub 3 just says this is the first value x could be. This is the second value x could be. This is the third value x could be. It's just a way of listing that we have multiple values that our random variable can be, and they're not the same. So they get a different subscript number to say, just as like a naming and a listing type of thing, saying these may be all different numbers, but they're all possibilities for x. The probability follows the same kind of naming convention. This is the probability that the first value of x occurs. This is the probability of the second value occurring, the probability of the third value occurring. So those subscripts just, it's a way of us listing this when we don't have numbers to put in the place, right? If we were to look at our previous set of values and probabilities, this would be x sub 1, x sub 2, x sub 3, x sub 4, p sub 1, p sub 2, p sub 3, p sub 4. But because we have numbers, we don't need to list it with the subscripts. We know what they are. The probabilities p sub I must satisfy two requirements, the same requirements that our probabilities had to fulfill in the previous chapter. All right, every probability p sub I is a number between 0 and 1. We know that to be true for probabilities. And the sum of the probabilities is 1. Right, so the sum of the probabilities for the outcomes of a random variable need to add up to 1. We have to account for 100%. To find the probability of any event, add the probabilities p sub I of the particular values x sub I that make up the event. All right, so for example, if we wanted to know the probability of tossing a coin and getting exactly 2 heads, right? There's only one outcome that fulfills that, and we have a 3 out of 8 chance of that happening. So we have 3/8 is the probability. If I wanted to know what's the probability of getting at most 2 heads, so I could have 0, 1, or 2, I would add up the probabilities, 1/8 plus 3/8 plus 3/8, because that's 0, 1, and 2, right? To get 7/8 probability of getting, tossing a coin 3 times and getting 2, 1, or 0 heads. Right? So the event, the probability of an event is the sum of the probabilities of the things that happen to make that event occur. Yeah. All right, so now we're going to talk about how do we find the mean, otherwise known as the expected value, of a discrete or random variable. Right? When analyzing discrete random variables, we follow the same strategy we used with quantitative data. You need to describe the shape, center, spread, and identify any outliers. Right? The mean of any discrete random variable is an average of the possible outcomes with each outcome weighted by its probability. All right. So what that means, we'll get to in a second. Okay, suppose that x is a discrete random variable whose probability distribution is same as we saw before. We have x sub 1, x sub 2, x sub 3, p sub 1, p sub 2, p sub 3. To find the mean or expected value of x, multiply each possible value by its probability. Then add all the products. Right. Notation-wise, it looks like this. Mu sub x, right, this is our little mu, our Greek letter, right, equals the expected value of x. That's what this e parentheses x is. That just, it's essentially mu sub x. It's another way of writing that, just not in Greek letters. Equals our first outcome times the probability of the first outcome occurring, plus the second outcome times the probability of the second outcome, plus the third outcome times the probability of the third outcome, and you just keep doing that until you run out of outcomes. Shorthand notation, we can use the summation notation, which is this capital sigma, it looks like an E, which says take the sum of all the outcomes multiplied by their probabilities. Okay, that's what the I represents, says I'm going to use all the X outcomes multiplied by their probabilities and add them all up. Right, so that's the notation. Right, this is slightly different than what we did for quantitative data, because in quantitative data, the only thing we have to do is add everything up and divide by how many things we had. And that's because typically we were talking about something where all the outcomes are equally likely. And so the calculation has to be adjusted because these things are not equally likely to happen. So now let's look at an example of how to calculate the mean or expected value of a discrete random variable. So we have this scenario, baby's APGAR score is the sum of the ratings of each of 5 scales, which gives a whole number value from 0 to 10. Right, let x equal the APGAR score of a randomly selected newborn. So we have our distribution, our probability distribution right here. There's a 0.001 chance of getting a 0, 0.006 of 1, 0.007 for 2, and so on through the list. We're going to compute the mean of the random variable x and interpret this value in context. Right. We see that 1 in every 1,000 babies would have an APGAR score of 0, 6 in every 1,000 would have an APGAR score of 1, and so on. So the mean expected value of x is given by the crazy formula here. Mu sub x equals the expected value of x equals the sum of x sub I times p sub I, which expanded says we take the first observation and multiply it by its probability, 0.001. Second outcome times the probability of the second outcome plus the third outcome times probability of the third, and so on until we get through all the possible outcomes where we have the last one is 10 times the probability of getting a score of 10. Push that all through our calculator and we get 8.128. Right? The mean APGAR score of a randomly selected newborn is 8.128. This is the average APGAR score of many, many randomly chosen babies. So this is what we would expect a score of about an 8 if we randomly selected many, 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 many babies. We would average right around 8. So next, we found the mean. Now we're going to do the standard deviation. Since we use the mean as the measure of center for a discrete random variable, we use the standard deviation as our measure of spread. Remember, those go together. The definition of the variance of a random variable is similar to the definition of the variance for a set of quantitative data. If you guys recall, when we're finding the variance for a set of quantitative data, we take the differences of all the observations from the mean and square it, and then we add those all up. That's our variance. We take the square root of the variance and we get the standard deviation. Similar thing applies here. All right, suppose that x is a discrete random variable whose probability distribution is as we've seen previously, and that mu sub x is the mean of x. The variance of x is given by this craziness. Right? We can use this notation here to represent the variance, where you just say var parentheses x. We can also use our sigma, just sigma squared sub x equals the first outcome minus the mean squared times the probability of the first outcome. So we're still using this idea of how far away is my outcome from the mean. Right, just when we have quantitative data, it's how far away is my observation from the mean. Now we're looking at the outcomes, and then we multiply by the probability of that outcome occurring. And we do this for each of our outcomes until we run out. If we want to do this in shorthand, we again use our summation notation, this Greek letter sigma, capital Greek letter sigma, times, right, x sub I minus mu sub x, right? Our outcome minus the mean squared times the probability of that outcome. Right? So that is our variance. But remember, once you find the variance, you have one more step to go. To get the standard deviation of a random variable, you have to take the square root of the variance. Right? So the workout for finding standard deviation is calculating the variance, because you need that to then put that underneath the square root sign and get the standard deviation. All right. And we'll see an example of this next. So back to our example with the APGAR score. We have the same kind of setting as before, same random variable of x. We're going to compute and interpret the standard deviation for our random variable. The formula for the variance is given as sigma squared sub x equals the summation of x sub I minus mu sub x squared times p sub I. Otherwise, the squared differences of all the outcomes minus the mean times the probability of each outcome. In this scenario, that gives us the following. All right, so the variance is equal to 0 minus 8.128, the mean squared times 0.001. Our second possible outcome minus the mean squared times the probability of that outcome. Right, and so on down the line until we hit all of our possible outcomes. And that yields us this approximate number of 2.066. And that is our variance. So again, we have one more step to go. We've done most of the calculation. The standard deviation of x is sigma sub x. Remember, that's our notation for standard deviation. Equals the square root of 2.066, which is equal to 1.437. So that means over many randomly selected newborns, the variance, or we would expect for the APGAR scores to vary by about 1.4 from the mean of 8.128 over many observations. Right. So a randomly selected baby's APGAR score will typically differ from the mean or vary from the mean of 8.128 by about 1.4 units. Okay. And it's important that we say by about, or by roughly, by approximately, because we are rounding this number. It is not exactly 1.4. It's 1.437 and probably a few more decimal places. So it's important to use that verbiage of about, approximately, roughly. All right. So we've been talking about discrete. Now we're going to move on to continuous random variables. Right. Discrete random variables commonly arise from situations that involve counting something, counting the number of heads when flipping a coin, counting the occurrence of a certain APGAR score. Right. Situations that involve measuring something often result in a continuous random variable, like measuring height, measuring distance, randomly choosing a number between 0 and 1. Right. A continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. So essentially, this is going back to our previous chapter about probability, and we're looking at density curves, right? The normal curve will come up again, all right? Table A, z-score, these things that we used last semester are coming back, all right? These cannot be displayed on a table because I cannot list all the possible outcomes. There's too many. There's infinitely many. Right? The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. Okay, that's discrete. I have a specific probability for each possible outcome. A continuous random variable y has infinitely many possible values. All continuous probability models assign probability 0 to every individual outcome. Only intervals of values have positive probability. So again, it's called continuous because there's an infinite number of possible values. Right? Even between 0 and 1, there's an infinite amount of values in that interval. No matter what number you give me, I can give you a number smaller than that within that interval. All right. Because of this, if I give a specific value in the interval and say, what's the probability of this? When referring to the density curve, that refers to a horizontal line in the density curve. A horizontal line has no width. So you're multiplying the height of that line by a width of 0. Anything times 0 is 0. Hence, the probability of a specific single event in that for that random variable is 0. We need an interval, a range of values to consider. All right. And don't worry, we'll do an example, which will hopefully make more sense of this. But so we need a moment to write anything down. So here's our example. We're going to looking at normal probability distributions for this one because they fall into the category of a continuous random variable. So the heights of young women closely follow the normal distribution with mean mu equals 64 inches and standard deviation sigma equals 2.7 inches. Now we're going to choose one young woman at random, call her height y. So the random variable y represents the height of a randomly selected young woman. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. All right. This is continuous because there's this range of heights, right? But no matter where we fall within there, there could be someone just slightly taller or slightly shorter. Right? There's an infinite number of possible heights. The problem we're going to answer is what's the probability that the chosen woman is between 68 and 70 inches tall? All right, so step one, we're going to state the distribution and the values of interest. Right, the height y of a randomly chosen young woman has the distribution of normal mu 64 standard deviation 2.7. Remember, that's what this notation shows. We have the n parentheses and two values. That's a normal distribution with a mean and standard deviation. We want to find the probability of y being greater than or equal to 68, but less than or equal to 70. So that's our interval. The lower bound is 68, the upper bound is 70. All right, so now we have an area under the curve. Come on, there we go. Next, we've got to do work. Right? We have to standardize the scores for the two boundary values. Right? And to do that, we have z equals the value, the outcome, the lower bound, minus the mean divided by the standard deviation. That's how we find our z-score. Z equals x minus mu divided by sigma equals 1.48. The upper bound gives us a z-score of 2.22. All right. We then take these values and go check out our table A. All right. Using table A, we get a bunch of the following values. All right. So here's a visual to see what we're looking at here. All right. If we're looking at our normal curve, good enough. Right, we'll have the mean right here, 1, 2, 3 standard deviations, 1, 2, 3. So this is positive. We have negative. Right, and then now that we have our z-scores, right, the lower bound is at 1.48, about right here. Upper bound is at like 2.22. So the area under the curve we're interested in is this little chunk right here. Okay. Now to get that using table A, recall that table A only tells us the proportion under the curve that is less than a certain z value. All right. So to find this interval, we have to find the probability that z is less than or equal to 2.22 and subtract the probability of z being less than or equal to 1.48. That gives us this little green area that I've shaded. All right. And that goes back to the fact that the first value we find, the 2.22, less than that gives us everything to the left. I don't need all of that. So then I find, okay, well, this is the area that's less than 1.48. When I subtract this other arrow, I'm only left with this chunk, which is what I wanted. So we get from table A, the probability of z being less than or equal to 2.22. So again, I went to table A, found 2 on the first left column, 0.2, then found 0.02 in the top column or top row, followed that to 0.9868. Same thing happened here, minus 0.9306. All right, and we get 0.0562. All right, and that essentially means that we have about a 5.6% chance of randomly selecting a young woman whose height is between 68 and 70 inches. If we just randomly pick someone, those are the chances that we pick someone between those heights. All right. Is there anything I can clarify?
I have a question.
Yes.
How did you get 0.9868 and 0.9306?
Okay. So that is from table A. So let me pull up table A. All right. So here's table A. This is the positive portion of table A. Right. So I need 2.22 and 1.48. So that means I'm going to find 2.2, 0.02, right? Because when I add 2.2 plus 0.02, I get 2.22. So now I find the intersection, and that's the 0.9868. Right. So there's that one. And then we have, was it 1.4, 1.48. So now I do the same and I say 1.4. I'm gonna have to scroll over. 8. We get 0.8 over here. And so we follow that. 1.48 and 0.9306. And those are the two numbers that we have here, 0.9868, right? Oops, right here, 0.9306.
Okay, thank you.
Okay, you're welcome.